What a beautiful signal. Today's experiment is inspired by a video on Pinehole Auto Diagnostics channel where Ivan got really alien looking waveforms from a liquid level sensor. They look like this. I hope you can see those. The link to the video is in the description. And I couldn't believe that these waveforms are coming from the sensor itself, because, well, first, BMW engineers are humans too, and second, there was no power feed to the sensor. So it looks like it's actually a microcontroller inside the evaluator box is probing the resistance of the sensor. Today we are going to reproduce the waveforms using a Pico arbitrary wave generator, and then we are going to reproduce the whole approach using an Arduino Uno microcontroller. Okay, in this experiment we are going to instruct our Pico arbitrary wave generator to generate regular pulses in the form of the square wave that will go to a small capacitor, 0.01 microfarad, then goes to the resistor under test and will sense voltage on channel A. We are going to set it up to plus minus 2 volts. Okay, let's do that. Plus minus 2 volts and 500 microseconds per division. Okay, now that we have that, let's see what we have in the circuit. So we do have the AWG, the red lead, connected via this wire to the capacitor, and we don't have any resistor at the moment, but we already have the channel A connected. So now we are ready to set up our arbitrary wave generator. So we are going to the signal generator dialog. So by default it's generating 1 kilohertz square wave, but we need something that is not as frequent, and let's put a trigger over here. And go to the arbitrary waveform generator dialog, where we'll have a square wave, 1 cycle, the minimum is 0 and the maximum is 1. Duty cycle we'll have set at 10%. Okay, now we are all good. Now let's bump up the amplitude to 2 volts, and this is what we have, a really nice almost a square wave. I guess because it's goes through the capacitor, it discharges a little bit on the oscilloscope input itself, but this is basically the voltage waveform that happens when there is nothing connected to the capacitor. But now we are going to use our capacitor that we have and see how the waveform changes. So I have 1 megohm here, and let me just connect it right there, and we'll see how the waveform changed. It changed only a little bit because 1 megohm is such a big resistance, but we can see that the slope has increased, so it goes down, decays faster than before. Also we have a more pronounced tail at the bottom. The next is 100K. So Let me put the 100K in, and here we go. Now we have a pretty nice picture where we have a decay quite rapid, but not enough to drop to half of the voltage. So you see that only at the end of the period, which is according to the cursors we have at 1 microsecond, no, 1 millisecond, only then it dropped to 900 millivolts. Okay, it's time for a 10K resistor, so let's just go and connect it. And what do we see? It's a beauty. We have a really nice spike when the square wave turns on, and a very nice decay all the way to 0. And when the square wave turns off, then we have a opposite spike when the capacitor discharges in the opposite direction. So it's all very nice, and maybe we can even take a look at how long it takes to halve the voltage from 2 to 1 volt. So let's move our cursors and see. What we get here is 85 microseconds. But what should it be in theory? We have a 0.01 microfarad capacitor, approximately, because it's never precise, and we have a approximately 10,000 ohm resistor. So what happens is, to halve the voltage, the time that should pass should be logarithm of 2 multiplied by resistance multiplied by capacitance. So that would be 0.7 multiplied by 10,000 multiplied by 0.01 multiplied by 10 to the power of -6. That's 0.01 microfarad for you. And once we do all the calculations, we get 70 microseconds. And on the screen we got 85 microseconds. Well, pretty close, not too shabby. It looks beautiful though. Anyway, so that's pretty good. Now, the last but not least is the 1K resistor. I expect to see even more rapid decay. And indeed, that's what we see. We actually have very fast decay. I don't know, it's hard to measure even. So this is obviously a very low resistance.